Hi friends, welcome to our YouTube channel Raj Academy. The main aim of this playlist is to teach and discuss the previous year gate questions of the network theory in a detailed manner. If you are seeing this video for the first time in the YouTube channel, then please do like, share and subscribe to the YouTube channel. And don't forget to press the bell icon button so whenever we upload a new video, the direct notification comes to your mobile. If any improvements needed in our lectures, then please do comment in the comment section and we will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. Up to previous lectures, we have discussed up to 105 numericals. So today the numerical is 106. See the question here. The question says that the Norton equivalent source in amperes as seen into the terminals X and Y is. Means this is a circuit. For this circuit, we need to figure out what is the current through the terminals X and Y, or it is called as the Norton current. The procedure for finding out the Norton current is we need to do the short circuit of the terminals X and Y, and then we need to figure out what is the value of the current in those terminals, and that's it. Let's solve this numerical. This is a diagram which is given in the question. So for this diagram, for this complex circuit, we need to figure out what is the Norton current through these terminals. So the procedure is first we need to do the short circuit. First we need to do the short circuit across these terminals, and then let me assume the current value is IN. IN is a Norton current, or it is also called as a short circuit current across the terminals. So we need to figure out by simplification. See here, this is a short circuit and there is a resistance of 5 ohm. So therefore the voltage across this 5 ohm is 0 because it is a short circuit. So the voltage across the 5 ohm is 0 means the current will be voltage by resistor. As the voltage is 0, so therefore the current in the 5 ohm is going to be 0 value. So therefore the current in the 5 ohm is 0. So by KCL what will happen is, by KCL the incoming currents is always equal to the sum of outgoing currents. As there are two currents IN and 0, so therefore the incoming current has to be IN. So this is the value. So therefore I am going to neglect this one because the current in this it is 0 ampere. So therefore I am going to neglect this branch. So therefore what I am going to get is, now this is a simpler circuit. So again I want to do the simplification of this circuit again. So what I am going to do is I am going to redraw the circuit so that it is very much clearly visible how to do more simplification. See here, this is a 5 ohm resistor with a voltage of 5 volt. And here there is a 5 ohm resistor with, I am writing it in this fashion, 2.5 ohm, and there is a voltage of 2.5 volt. And these are the terminals X and Y. So these terminals I am going to do the short circuit, and then I need to figure out what is this Norton current. So what I am going to do is I am going to find what is the Thevenin equivalent across these terminals. I am going to find what is the Thevenin equivalent. So in order to find that, so I am going to replace this circuit with a voltage source and a resistance. So what I am going to do is I am going to find what is the voltage across this one. This is called a VTH. So 5 volt is going to distribute across the 5 ohm and 5 ohm. As these two resistors are equal, by voltage division VTH will be half of the supply voltage. So therefore 5 by 2 is equal to 2.5 ohm. 2.5 volt. So now I need to find what is the Thevenin resistance across these terminals. So the procedure is, in order to find what is the Thevenin resistance across these terminals, we need to do short circuit of the ideal voltage source and open circuit the ideal current sources. As there is only one ideal voltage source in this circuit, so therefore I am going to short circuit the ideal voltage source, and then I am going to figure out what is the equivalent. I am going to figure out what is the equivalent resistance or Thevenin resistance across these terminals. As the 5 ohm and 5 ohm are contained in parallel, so therefore the Thevenin resistance is equal to 5 parallel 5. It will become 2.5 ohm. So therefore what I am going to do is I am going to replace this complex circuit with a simpler circuit of Thevenin resistance and a Thevenin voltage. So therefore now the circuit is simpler, like this is the Thevenin resistance. The Thevenin resistance is 2.5 ohm and the Thevenin voltage. The Thevenin voltage is VTH is equal to 2.5 volt. this is simpler circuit, so I am going to join this simpler circuit to the original circuit, and then I need to figure out what is the value of the IN. See, the IN is whatever the current IN has to go in this branch also, as there is no other branches, so therefore the same current will go here also. So by KVL I am going to write a KVL across this loop. So therefore I am going from lower potential to higher potential, so therefore there is a rise in potential which is 2.5, and I am going from plus to minus. As these two resistors are connected in series, I am going to, as these two resistors are connected in series, the equivalent resistance will be sum of their individual resistance. So therefore 2.5 plus 2.5 will become 5 ohm. So therefore this will be 5 ohm, right? 5 ohm. So always current goes from high potential to low potential, so therefore there is a drop in potential, so minus 5 into IN. And similarly from here I am going from plus to minus, means there is a decrease in potential, means minus 2.5. so therefore as there is a closed loop, so here this plus 2.5 minus 2.5 will get cancelled, so therefore IN is equal to 0 ampere. So this is the Norton current. This is the Norton current across the terminals X and Y. So the procedure is, first we need to do the short circuit across the terminals, and then we need to find what is the value of the current which is flowing through those terminals. So we figured that the value of the current, Norton current, is 0 ampere. This is the required solution. Okay, now we will move forward to solve the numerical. The numerical number is 107. See the question here. The question says that assuming an ideal transformer, the Thevenin equivalent voltage and the impedance as seen from the terminals X and Y for the circuit in given figure. So there is a transformer in the circuit, and we need to figure out what is the Thevenin voltage and the Thevenin impedance across the terminals X and Y. And this is a very easy numerical. Let's solve this numerical. So this is an ideal transformer with a turns ratio 1:2, and these are the terminals X and Y, and there is a resistance of 1 ohm, and there is a sinusoidal supply source of sin omega t. So we need to figure out what is the Thevenin voltage and the Thevenin impedance across these terminals. So what I am going to do is, the procedure is, first we are going to figure out what is the Thevenin voltage. So first, in order to find Thevenin voltage, here let me assume this is the voltage VTH, because this is an open circuit, so therefore the current here is equal to 0. Let me assume this is I2 is equal to 0, because this is an ideal transformer. In ideal transformer, whenever the output current is 0, so therefore the input current also has to be equal to 0. This is only in ideal transformer, but it is not in case of practical transformer. But in practical transformer, even when the output current is 0, there will be a certain small current, input current. But only in ideal transformer, whenever the output current is 0, then the input current is also equal to 0, only in case of ideal transformer. But in practical transformer, even when the output current is 0, there will be a small amount of input current. So what I am going to do is, here let me assume this is a V1. This voltage, let me assume this voltage has V1. So therefore, if you see carefully, the current in this 1 ohm resistance is 0. So therefore, there is no drop of potential across this 1 ohm. So therefore, the input, supply input voltage has to be equal to the induced voltage. So therefore, V1 is equal to sin omega t. So we need to figure out what is the Thevenin voltage. So Thevenin voltage we need to figure out. See, the basic transformer is, the voltage ratio has to be equal to the number of turns ratio, means the ratio of V1 by V2. V2 is the voltage, Thevenin voltage. So this is the induced EMF in the primary, or let me assume here E1 by E2. E1 by E2 is equal to N1 by N2. This is the standard value. Here let me assume this as a V1, because it will be very easily understandable. So therefore E1 by E2 is equal to turns ratio N1 is to N2. Here N1 by N2 is equal to 1 by 2. So therefore 1 by 2. So here E2 is equal to VTH, E1 is equal to sin omega t. So therefore sin omega t by VTH is equal to 1 by 2. So therefore the Thevenin voltage is equal to 2 times of sin omega t. So what I am going to do is, I am going to replace this complex circuit with a simpler circuit. The simpler circuit has a voltage. The simpler circuit has a voltage VTH. VTH value is equal to 2 sin omega t. this is a simpler circuit, and we need to find what is the here ZTH, the Thevenin impedance we need to find, and this is a X and this is a Y. So these two circuits are going to give a same amount of power to the output. Here whatever the output you connect in this one and in this one, both will receive same current, same voltage and the same power. That is the meaning of the equivalent circuits. So now we will figure out what is the value of the Thevenin impedance. Now we are going to find what is the Thevenin impedance across the terminals X and Y. So what we are going to do is, now here we need to find what is the Thevenin impedance. The standard procedure is, first we need to do remove the ideal current sources and ideal voltage sources. Means we need to short circuit the ideal voltage source and then open circuit the ideal current sources. There is only one voltage source, so therefore I am going to short circuit this one. I am going to short circuit, there is only one ideal voltage source, so therefore I am going to short circuit this input terminal. So now this 1 ohm I am going to transfer it to the secondary. So the basic formula is, whenever if you want to transfer this 1 ohm to the secondary, the basic formula is Z1 by Z2. Here I am transferring from here to here, right? So therefore Z2 is equal to Z1 into, because I am transferring to secondary side, so it will be N2 by N1 whole square. So therefore here Z1 is the 1 and N2 is here this one, secondary term. So 2 by 1 whole square. So therefore 4 ohm. See, whenever if you are transferring from primary to secondary, means now this is going to be equivalent to like this one, like 4 ohm. This is the equivalent here, X and Y. So these both circuits are equivalent in terms of the impedance value. Means I am going to transform this primary impedance to the secondary impedance. So therefore this is the equivalent circuit you will get in terms of impedance values. So therefore the Z2 is equal to 4 ohm. Z2 means this is the Thevenin impedance. So therefore the Thevenin impedance is 4 ohm. So this is the 4 ohm. So this is the equivalent circuit across the terminals X and Y. So the Thevenin voltage is 2 sin omega t and the Thevenin impedance is 4 ohm. This is the required solution of this numerical. Okay, now we will move forward to solve the numerical. The numerical number is 108 here. See the question here. The question says that in the circuit shown below, if the source voltage Vs is equal to 100 angle 53.13 degree voltage, then the Thevenin equivalent voltage in volts as seen by the load resistance RL. So in this circuit they are given the source voltage also, and then we need to figure out what is the Thevenin voltage as seen by the load resistance. And it is very simple problem. Let's solve this numerical. See, I have drawn the figure again. See here, this is the load resistance 10 ohm and this is the resistance of 3 ohm and the impedance is J6 ohm. This is a voltage dependent voltage source or voltage controlled voltage source, because the value of this voltage is dependent on certain value, which is a voltage value. That's why it is called as a voltage controlled voltage source. This is called as a current controlled voltage source because I2 is the current, so this current value is controlling the voltage, so therefore current controlled voltage source, and this current I2 is the current flowing in this circuit I2. So we need to find what is the Thevenin voltage across the load resistance. So the standard procedure, in order to find the Thevenin voltage, first we need to remove this resistance or the load, we need to remove it, and then we need to figure out what is the Thevenin voltage. So let me assume the voltage here VTH. This is the voltage we need to figure out, because in every standard procedure is, whenever if you want to figure out what is the Thevenin voltage across any particular load, then first we need to remove that load and then we need to keep here VTH, and then we need to figure out by doing some simplification, then we need to figure out what is the value of the VTH. If you see carefully here, this is an open circuit because this is a terminals are open, so therefore this is an open circuit, so therefore the current in any open circuit, the current I2 value will be equal to 0 because it is a open circuit, so therefore I2 is equal to 0. See, this voltage source value is dependent upon this current value, so therefore as I2 is equal to 0, therefore 40 into I2 will become 0 volt. So therefore simply it means that this is a short circuit because the voltage itself is 0 volt, so therefore we can write it as a 0 volt. So if 0 volt is also called as a short circuit, so therefore I am going to short circuit this current control voltage source. See here, as the current is 0, so therefore here as the current is equal to 0, so therefore there is no voltage drop in this one, because the voltage drop will be 0 here. So whatever the supply, whatever the voltage by this voltage control voltage source has to be equal to the VTH, because there is no voltage drop here. By KVL also we can write here closed loop KVL and the drop is here 0, so therefore this voltage value is equal to this voltage value. So therefore VTH is equal to 10 times of the VL1. So if you figure out what is the value of the VL1, then we can easily find what is the value of VTH. So the VL value here, the VL value is the voltage drop across the impedance. So therefore this is a simple RL circuit. So here by voltage division VL1, see voltage division VL1 is equal to here the supply voltage into the impedance is J4, right? J4 by the total impedance 3 plus J ohm. This is the voltage VL. So the VS is equal to, VS is equal to 100 angle 53.13 degree into J4 by 3 plus J4. If you do the simplification, here VL1 we will get VL1 is equal to the voltage drop across the inductor J4 ohm, we will get here 80 angle 90 degrees. This is the value which we will get. See here VTH value is equal to 10 times of VL1. So therefore the VTH is equal to 10 times of the VL1. So therefore it will become 800 angle 90 degrees. So therefore the Thevenin voltage is equal to 800 angle 90 degree volt. This is the required solution of this numerical. See the standard procedure, whenever if you want to figure the Thevenin voltage, first we need to remove that load and we need to name it as a VTH. As here this is an open circuit there, so therefore the current is equal to 0. As this current is equal to 0, this value will be 0 because it depends upon this value I2. So therefore this value now VTH is simply depends upon this voltage control voltage source value. So therefore if you figure out what is the VL1, then we can easily figure out what is the value of Thevenin voltage. So by this circuit I figured out what is the value of VL1 and then I easily figured out what is the value of the VTH. So now we are going to discuss about the 109 numerical. See the question here. The question says that a source Vs of t is equal to V cos 100 pi t as an internal impedance of 4 plus J3 ohm. If a purely resistive load connected to this source has to extract the maximum power out of the source, its value in ohms should be. Means there is a voltage source value is given in this question, and also the internal impedance of the source is also given. So therefore now we need to connect a resistor R so that it can draw the maximum power out of the circuit. So let's solve this numerical. So before solving this numerical, let me tell you a small concept here. So with this concept we can easily solve this numerical. See here, this is a circuit. In this circuit there is a voltage source. This is a AC voltage source. Here Vs represents the RMS value. It is not the maximum value. It is always Vs is the RMS value. So therefore this is the here internal impedance of this source, ideal voltage source. Here Zs is equal to Rs plus Jxs, and this is the load ZL is equal to RL plus Jxl. Here for maximum power transfer, always the load has to be a variable, means the impedance of this has to be variable value and this Zs has to be fixed value. Then only the maximum power transfer will be applicable. Suppose here ZL is a fixed value and if Zs is a variable, then always choose the minimum Zs. So therefore the current in the circuit will be a maximum value. So therefore the power transfer to the load will be maximum because the current is maximum. So always for maximum transfer theorem will applicable when ZL is variable and Zs is a constant value. So therefore let us assume this Vs is constant and Zs value is a constant value, but ZL is a variable value. So RL can be variable or whether XL can be variable or both can be variable. So let us see what are the conditions for maximum power transfer to the load. Because see here, suppose if you want to figure what is the value of the current, and we can easily figure the value of the current and also the power in this load, only the RL part will consume the active power because only the resistor part will consume the active power, but the inductor value doesn't consume any active power. So therefore it means directly we are figuring out the maximum power which is taken by this resistive load. So therefore, when suppose let me assume only RL is a variable, means XL is a fixed quantity. Let me assume that one. So therefore, when RL is equal to root over RL square plus XS plus XL whole square, at this value of the RL, the maximum power will be transferred from the source to the load only at this condition. So suppose let me assume only when XL is a variable, means then RL has to be equal to constant value. Let me assume like that. Then at this particular value of XL, when XL is equal to minus XS, so therefore the in this case the circuit will be purely resistive. So therefore the maximum power transfer to the load only when XL is equal to minus XS, only when XL is variable and RL is a constant value. Suppose let me assume when RL and XL are variable, means both are variable, so therefore the load impedance is also variable. At that condition, the maximum power will be transferred only when ZL is equal to ZS conjugate, means if you do the simplification here, RL is equal to RS and XL is equal to minus XS. At this condition also the circuit will be purely resistive. So let me assume another case. Suppose when RL is variable and XS is 0, means simply we can put here XS is equal to 0 and XL is equal to 0. Here XL is equal to 0 and I am keeping here as, if you keep here XL is equal to 0, then we will get root over RL square plus XL square. So therefore RL is equal to, at this value of the particular value of the resistance, the maximum power will be transferred from the supply to the load. See, this numerical is also based on this concept only. So here they have given impedance value and only the load resistance is going to connect. So therefore at this particular value the resistor RL, root over RL square plus XL square, then we are going to get the maximum power which is transferred from the source to the load, and only in the load only the resistive part is going to consume the active power. Whatever the power which is transferred from the source is going to consume only by the maximum power. That maximum power is going to absorb only by the resistive part which is RL. So now we are going to solve this numerical. I have drawn the figure here. So the supply voltage value is equal to V cos 100 pi t, and the internal impedance of this source is ZS is equal to 4 plus J3 ohm. So now we are going to figure out what is the value of the RL. So therefore the maximum amount of power is transferred from source to the resistive part RL. So therefore I have already told you at this value of the particular resistor RL is equal to root over RS square plus XS square. So this RS and XS are the internal impedance, resistance and the reactance. RS is equal to 4 square plus 3 square. So therefore if you do then it will get 16 plus 9 means 25, root over 25 means at 25 ohm. So RL is equal to at 5 ohm, then we will get the maximum amount of the power is transferred from the source to the load. This is the required solution of this numerical. So now let's solve the numerical 110. See the question here. The question says that assuming both the voltage sources are in phase, then the value of the R for which maximum power is transferred from circuit A to circuit B. Here there are two circuits are given, and we need to figure out what is the maximum amount of power is transferred from circuit A to circuit B. So therefore that particular value of resistor we need to figure out in this question, and so very interesting concept. So listen very carefully. This is a circuit I have drawn in this figure. Here see here, this is a circuit A which has a 10 volt source and there is a resistance of 2 ohm. This is circuit B, it has constant resistor R and minus J, capacitor value is minus J ohm, and there is a source value. This source is a AC source, so therefore the voltage across the source is 3 volt. It's like RMS value. So now we need to figure out what is the maximum amount of power is transferred from circuit A to circuit B. So these are the terminals, right? Across these terminals the power is transferring from circuit A to circuit B. So what I am going to do is, first we need to simplify the circuits. The circuit A and circuit B, we need to simplify these two circuits in a fashion of Thevenin voltage and the Thevenin impedance. So what I am going to do is, I am going to open these terminals and I am going to figure out what is the Thevenin impedance and Thevenin voltage across these terminals. Because the circuit is a very simpler circuit in the fashion of Thevenin voltage and Thevenin impedance, so no need to further simplify this circuit A. But if you see circuit B, here now we need to figure out what is the Thevenin voltage and Thevenin impedance across these terminals. So what I am going to do is, for the first procedure is I am going to find what is the value of the Thevenin voltage. So I am going to find what is the Thevenin voltage means so open circuit terminals, right? Open circuit terminals means the current here in this one is equal to 0. So therefore the what is the voltage drop across the resistor has to be equal to 0. So whatever the Thevenin voltage has to be equal to the supply voltage. So therefore I am going to simplify this circuit into a fashion of the Thevenin voltage and Thevenin impedance like equivalent circuit. So what I am going to do is here Thevenin voltage across the terminals is equal to 3 volt. So now I want to figure out what is the value of the Thevenin impedance. Thevenin impedance across these terminals means the standard procedure is first we need to remove the ideal voltage source and the ideal current source. Means ideal voltage source has to be equal to short circuit and ideal current source has to be equal to the open circuit. Here there is only ideal voltage source, so therefore I am going to short circuit this one. See, whenever the two resistors are equal to parallel means R1 R2 by R1 plus R2 or impedance is Z1 Z2 by Z1 plus Z2. As Z1 is equal to 0, so therefore 0 into Z2 by 0 plus Z2 will be equal to 0. So therefore the net impedance of these two parallel combination will be equal to a ideal conductor means pure resistance has to be equal to 0. So therefore now the Thevenin impedance across these terminals is equal to R. So therefore the Thevenin impedance across these terminals is equal to R. So what I am going to do is this complex circuit I have transferred to a simpler circuit. This circuit B is consists of a 3 volt and a resistor R. So therefore this is a circuit B. Now the circuit A we know already. Circuit A is here consists of only 10 volt and this is circuit B, right? This is circuit B and this is a circuit A. The circuit A consists of the 2 ohm resistor and a 10 volt source. 10 volt source. So this is circuit A. So now I am going to find what is the maximum power which is transferred from circuit A to circuit B. This is circuit A and circuit B. So what I am going to do is I am going to assume this as a voltage V and this current I, because from these terminals voltage and current only the power is transferred. So therefore this power is equal to voltage into current. So therefore I have to find the value of the V and I in terms of R. So therefore if you differentiate the power with respect to a resistor, then we will get the maximum amount of power is transferred from circuit A to circuit B at a particular value of R. So therefore what I am going to do is this circuit is a series circuit. The same current I is flowing through the whole circuit. So I am going to write a KVL in this loop. So by applying the KVL here, I am going from minus to plus, means there is a rise in potential plus 10, and I am going from plus to minus. Current always goes from positive to negative. So therefore there is a drop in potential minus 2I. And similarly here also current goes from positive to negative, so therefore minus RA. Here I am going from plus to minus, so therefore there is a drop in potential. Minus 3 is equal to 0. So 10 minus 3 is 7 is equal to I common 2 plus R. So therefore I is equal to 7 by 2 plus R. This is the value of the current. So this is the current I is equal to 7 by 2 plus R. So now I want to find what is the value of the voltage V. Means I am going to go in this KVL loop. So in this KVL loop, in this loop I am going to write the KVL. So I am going from minus to plus. So therefore there is a rise in potential, and from plus current goes from high to negative. So therefore high potential, low potential. So therefore there is a drop in potential minus 2I, and plus 2 minus means there is again drop in potential. Minus V is equal to 0. So therefore the V is equal to 10 minus 2I. So we know the value of the current I. Current I is equal to 7 by 2 plus R. So therefore 10 minus of 2 of 7 by 2 plus R. So if you simplify this one, we will get 10 minus 14 by 2 plus R. Means we will get 20 plus 10R minus 14 by 2 plus R. So finally we will get 10R plus 6 by 2 plus R. So this is the value of the voltage. The value of the voltage is 10R plus 6 by 2 plus R. See, we got current I is equal to 7 by 2 plus R and V is equal to 10R plus 6 by 2 plus R. So this voltage and this current we have replaced in terms of, means we have made these terms in terms of R value. See, the power transfer from circuit A to circuit B means the power is equal to voltage into current, right? So therefore the power is equal to the voltage into current. So I am going to multiply this one. See, 10R plus 6 by 2 plus R into 7 by 2 plus R. So if you do this one, we will get 70R. 70R plus 6 on the 42 by 2 plus R whole square. This is the amount of power. So therefore P is equal to 70R plus 42 by 2 plus R whole square. So now we need to figure out what is the at particular value of resistor. This power has to be a maximum value. Means here see, suppose let me assume this is a resistor R x-axis and this is a y-axis P. So if you vary this R value from 0 to, if you vary this from R0 to some particular infinity, then the curve will be like this in this parabola fashion, in this down parabola fashion. So therefore in this fashion the curve will be there. So at this resistor, at this particular resistor, let me assume this is some R at this particular resistor R, the power is maximum. So therefore the slope across this value is equal to 0, means dp by dr has to be equal to 0 across this point. So that is what I am going to do here. dp by dr is equal to 0. So if you do the simplification, so let me do this one simplification here. This is u by v, right? u derivative into v minus u v derivative means this one into 2 plus r by v square. V square is 2 plus r whole square will become 4. So if you equate to 0, then this term has to be equal to 0. The upper part has to be equal to 0. So I am doing it directly here. So therefore this term will go to the right side, it will become 0. So if you simplify this whole thing, we will get r is equal to 0.8 ohm. This is the required solution of this numerical. So let me tell you the summary of this numerical. First thing is we need to simplify the circuit A and circuit B. The power is voltage into current, right? So therefore we need to figure out what is the value of the resistor R. So therefore what I am going to do is I am going to make this voltage in terms of the resistor and current in terms of resistor, and then power is equal to voltage into current, and then for particular resistor means dpr by dr is equal to 0. So slope has to be equal to 0. So therefore dpr by dr is equal to 0. By simplifying that one, we will get finally R is equal to 0.8 ohm. So let me tell you another method also to how to solve this numerical. Say this circuit A is 10 volt and 2 ohm are the simplified value, and circuit B also has simplified in terms of voltage 3 volt and resistor R. So what I am going to do is, now I am going to do this in a very easy manner. See this 3 volt, right? This is a 3 volt. The current is I. Let me assume the current in the circuit is I. So therefore the power consumed by the 3 volt source. How much is the power consumed by this 3 volt source? So therefore power is equal to voltage into current. So the voltage is 3 and the current is I. So the power consumed by the 3 volt source is 3I. So what I am going to do is I am going to replace this ideal voltage source to a resistor. Means that resistor also has to absorb the same power. So therefore I am going to replace this ideal voltage source by a resistor. Let me assume the resistor value R2. Let me assume the value of the resistor R is, let me assume it is R1 also. R1. So therefore this R1 also has to absorb the same power. So therefore is equal to the current is also say I and the resistor is R1. So therefore I square R1. So therefore now if you simplify, it will become 3 is equal to I into R1. So therefore R1 is equal to 3 by I. So therefore the value of the resistor is 3 by I. So now this resistor and resistor are in series fashion. So therefore the net resistor will be R plus 3I, because the net resistor is R plus 3 by I. This is the net resistor. So therefore this is the net resistance of the circuit B. This is circuit B, right? This is circuit A and this is circuit B. This is circuit A and circuit B, right? So this is the net resistor of the circuit B, R plus 3 by I. But we know one thing, in maximum power transfer, the maximum power transfer will transfer from circuit A to circuit B only when this load resistance value is equal to the internal impedance value. So therefore internal impedance is 2 ohm and RL is equal to R plus 3 by I. So now there is only one equation with two unknowns, R and I. So we need to find one more equation. So therefore we can easily figure out what is the value of the R. So this equation is for the maximum power transfer. So when RL is equal to RS, RL is this one and RS is this one. So now I want to figure out another equation, right? So another equation is just like the KVL across this loop. So therefore 10 is equal to, let me write here another, this is a equation 1 and this is a equation 2. So supply voltage is 10 volt, right? I am going from KVL, minus 2 plus means 10 volt. So I am going from positive to negative, here also same positive to negative. So therefore here I will get here minus 2i minus I of R plus 3 by I is equal to 0. This is another equation, right? So I will get 10 minus 2i minus Ri minus 3 is equal to 0. But here 10 minus 3, 10 minus 3 is 7. 7 is equal to I of 2 plus R. But we know I is equal to, suppose here if you want to figure out what is the value of the current I, then we will get here 2 minus R is equal to 3 by I. So therefore I is equal to 3 by 2 minus R. So simply keep it here, I is equal to 3 by 2 minus R into 2 plus R. So now we will get here 7 to the 14 minus 7R is equal to 7, 3 to the 6, 6 plus 3R. So therefore if the 6, if you go to the left side, it will become 14 minus 6. 14 minus 6 is equal to 3R plus 7R. So it will become 8. 8 is equal to 10R. So therefore R is equal to 0.8 ohm. So in this fashion also, we figure the value of the resistor R. This is a very easy manner. See, I will tell you again. See, the 3 volt source will absorb the power 3I. So I am going to replace this voltage source by a resistor R1. So therefore I square R1, both has to absorb the same power. So therefore R1 I have figured out. R1 is equal to 3 by I. So here I made an equivalent part. This resistor and this resistor I made an equivalent part R plus 3I. This is the equivalent resistors of the circuit. Means this is the equivalent circuit of circuit B. So this maximum power will transfer only when the load resistor is equal to source resistor. So this is the, by this way I figured one equation. But in this way I have figured what is the value of the I in place of R. So this is a simplified version. Now I wrote the KVL across this loop. Then I figured the value of the current. Current I is equal to 7 by 2 plus R. So in place of I substitute that value and then we figure out the value of the resistor. R is equal to 0.8 ohm. This is the another fashion in which way we can solve this numerical. So by this lecture we have successfully completed 110 numericals of network theory which are the previous year gate questions. If you are seeing this video lecture for the first time on our YouTube channel, then please do like, share and subscribe to our YouTube channel and don't forget to press the bell icon button so whenever we upload a new video that direct notifications comes to your mobile. If any improvement is needed in our video lectures, then please do comment in the comment section, then we will definitely include all those improvements in the coming lectures. Thank you for watching for our lecture. Keep smiling, take care and bye bye.